Continuing our discussion of electrophilic aromatic substitution reactions, we're now going to consider what happens when these reactions occur on a monosubstituted benzene, a benzene with one substituent. So for instance, we could consider nitration of benzene. Where we add a nitro group to benzene. But what if we instead did this to toluene where there's already a substituent there? Well, one observation that is made when you run this reaction is the toluene reacts faster. So the presence of the methyl group makes the reaction go faster. We say that the methyl group is an activator. The other observation that you have is that the nitro group could add ortho, meta, or para to the methyl group that's already there. And we see that the majority of product is ortho or para. Very little is meta. So we say that the methyl group is an ortho-para director. So when we have some substituent X already on the ring and we add an electrophile, we ask ourselves two questions. Is the substituent already present activating or deactivating? And the other is whether that substituent is a meta-director or an ortho-para director. And we see here in this diagram that relative to benzene, we have activators and we have deactivators. The deactivators have reactivity that is slower than benzene. Activators have reactivity that is faster than benzene. And when we think about the explanation for these abilities to be an activator or deactivator, we ask ourselves, does the substituent donate electron density or withdraw it from the ring? If it donates electron density to the ring, it makes the ring a better nucleophile, the reaction goes faster. But if the substituent withdraws electron density, it makes the reaction go slower. Then you have the directing group ability. You'll notice that all activators are ortho-para directors. All deactivators are meta-directors with one exception, halogens. Halogens are ortho-para directors. And when we consider the directing group ability, we're going to try to make arguments for why something is an ortho-para director versus a meta-director. And what we look at is locations on the ring relative to the substituent. Are they stabilized or destabilized in the intermediate? So we turn to the intermediate when trying to make explanations for why something is an ortho-para director versus a meta-director. So activating groups donate electron density to the ring. So something like a hydroxyl group is an activator. It donates electron density to the group or to the ring. We'll see that in a minute. And we see that the reactivity is 1,000 times greater than that for benzene. So these relative rates are for nitration, but we could make similar comparisons with other types of electrophilic aromatic substitution. We could do nitration, bromination, adding a bromine to the ring or a nitro group for nitration. But whatever type of electrophilic aromatic substitution we do, an OH will make the ring go faster compared to just hydrogen. Likewise, deactivators withdraw electron density from the ring. So for instance, a chlorine on the ring will make the reaction go more slowly than if it was just hydrogens. So again, these relative rates are for nitration, but no matter what type of substitution you're doing, the chlorine will make the ring react more slowly compared to hydrogen. There are two ways in which electron density can be donated or withdrawn. They are inductive effects and resonant effects. So for inductive effects, we're comparing to benzene, where every carbon has a hydrogen. Alkyl groups are inductively electron donating, and we saw that with carbocations when we did alkene addition reactions. The more alkyl groups, the more stable the carbocation. So for the same reason, these alkyl groups are donating electron density to the ring. There's a larger pool of electron density on an alkyl group than there is a hydrogen. That's able to stabilize a carbocation, it's able to stabilize an alkene, pi bonds, and it's able to donate to the aromatic ring and make it more reactive. Now, if you have an electronegative atom, that's going to have the opposite effect. It's going to pull electron density away from the ring. So this is donating, this is withdrawing. And these are also withdrawing. A nitro group with its electronegative nitrogen and the positive charge is going to pull electron density away. If you have something like an aldehyde, that carbon is slightly positively charged because of the presence of the oxygen. So that's going to pull electron density away. Now the other way in which you can have electron donation or withdrawal to the ring is through resonance effects. So here we can look at chlorine or oxygen on the ring, and you can draw other resonance structures. So for instance, these electrons can become a pi bond here, and these electrons have to go somewhere, so you can kick them up onto this atom. And then you could move these in to become a pi bond here and kick these up onto this carbon. And then likewise, you could move these here and kick these up onto this carbon. And the overall effect is that we have moved electrons into the ring You can do the same for the chlorine. You can try that on your own. Draw some resonance structures where you show electrons being moved into the ring. So the overall effect is that electrons are donated to the ring. Resonance effects can also withdraw electron density from the ring. So for instance, take this nitro group. We can move these electrons up here, kick these onto the oxygen. That nitrogen's still positive. And that's going to create a carbocation. And then we can move the carbocation around the ring. And all these we're going to have a pi bond. These will remain unchanged now. So we can move a pi bond there. We can move the pi bond here. And the net effect is that we've removed electron density from the ring. So, to summarize, I'll use W for withdrawing and D for donating. Alkyl groups inductively donate. There is no resonance effect. And so overall, it's donating. Something like a nitro group or an aldehyde, we saw withdraws inductively and also through resonance. And so it is strongly withdrawing. Halogens and things like oxygen or nitrogen with their lone pair, like an amino group, not a nitro group, like an amino group, like NH2 or an OH, or halogens, they inductively withdraw because of electronegativity, but they donate through resonance. And so you have the same effects through inductive effects and resonance effects for both of these. So why did I separate them? Well, it's because obviously the overall effects will be different. It's the relative strengths of these. Halogens are strongly withdrawing through induction, whereas these other groups are strongly donating through resonance. So the overall effect is withdrawing for halogens, but donating for the other groups. So the net effect is different as far as donating or withdrawing from the ring and activation or deactivation abilities. So we have this line here. We're just talking about activation, deactivation. These are activators. So you have things like alkyl groups that inductively donate, things with lone pairs like an oxygen or a nitrogen with its lone pair. They donate through resonance. They withdraw by inductive effects because of electronegativity, but the effect is stronger through resonance. Halogens, they are strongly withdrawing by the inductive effect, so it's mostly about the electronegativity. The lone pair that can donate through resonance is a weaker effect for halogens. So they're deactivators. And then these groups where you have like a nitro with a positive on the nitrogen, or cyano, I should mention if you had something like this, like a CF3, that would be inductive only. Inductive withdrawing effect because of the fluorines on the carbon. They would be inductively pulling electrons out of the ring because of electronegativity, but there's no resonance effect. So that would be another case of a deactivator.